Okay, thank you very much. I had some last-minute doubts about how to structure this lecture. So the first part will be, very elementary from another theory perspective, meaning, it's sort of, for elementary school kids, like we know what the arithmetic. But maybe, there'll be some obvious symplectic geometry and topology in it. And then we will switch something that has a slightly more number theory in it. Okay? And just in case you're a number theorist, this is the proof that later there will be some number theory. Okay? Which I will now hide until I need this. So, if I have a symplectic manifold, there is a basic invariant which is quantum homology. Which is just the ordinary homology, but with a product formed by contributions from holomorphic maps. And as in ordinary homology, you can use to work with different coefficients. Let me just do a field. All right. So the example. Oh, by the way, if you wonder about holomorphic maps, well, you could think of this as being an actual complex algebraic variety, and then you know what a holomorphic map is. If it's not, then you have to choose an almost complex structure, and it's they're pseudo-holomorphic maps in the sense of problem. But, no worries. So in this case here, okay, and the quantum product sets a squared equals to 1, so it doesn't actually respect, this is degree 2, it doesn't actually respect the degrees, okay? So in other words, this is the ring with the generator A, and a squared equals to 1. Okay, now I want to point out something to you, which is fairly obvious, so which is that, if the characteristic of K is not equal to 2, then this ring is semi-simple. So it's actually, so you have two idempotents. One plus minus a over 2. So they satisfy, and they are mutually orthogonal. So these idempotents decompose it into a sum of two copies of the field. On the other hand, if the characteristic of K is 2, then, well, this is somewhat different. So in fact, if I said B equals A 1 plus A, then this ring here so it has actually this nilpotent element because a squared, well, plus or minus are the same. A squared minus 1 is the same as a minus 1 squared or a plus 1 squared. Okay, I have slightly space here. Okay, so so this is the symplectic geometry. I am going to use sort of mirror symmetry to translate these things into, so mirror symmetry doesn't always apply. It applies to symplectic manifolds with a certain structure. When it applies, it transforms questions into questions of algebraic geometry. It's, you have to get used to how exactly it does that. We of course had now 25 years or so to get used to it. It's not absolutely essential for what I'm trying to say, but on the algebraic geometry side, things tend to be slightly more familiar. Okay?
So,
yes?
In what sense is this example, the product is deformed by contribution from holomorphic maps? In what sense?
Well, there is a, so in the ordinary, the ordinary cup product has a squared equals to 0.
Right.
Okay?
So, but in what sense is this?
Yeah, 1 second.
Okay.
I'll just get there. Okay? So, in this case here, M is S2, which is also the same as CP1. So there is an obvious holomorphic map from CP1 to it. Okay? And when you try to figure out the coefficient of this A squared, what you're asking is fix 3 points on your target manifold, and how many holomorphic curves are there going through these 3 points? In this case here, exactly 1, so that makes it 1.
Passing through, you mean like 0, 1, infinity?
0, 1 in infinity, yeah, well, in this case, it's too tautological to actually be very, instructive.
You have to be precise with maps because you have a lot of automorphisms.
You have to be precise by what you mean up to what automorphisms and so on. So that you fix 3 points on your target manifolds, and you have a map which maps 0 to one of the points, 1 to the second point, and infinity to the third point.
Yeah.
Okay, and in this case here, well, no matter how you fix the points, there would be a unique such map, so it's 1. Okay? So mirror symmetry, so if we take this S2, there is, the mirror is a function, okay, the superpotential, not particularly instructive because so many things in physics are called superpotentials. So W, okay, so it's a function from Gm to the affine line, or other words, it's a Laurent polynomial, in this case here, 1 variable. Okay. And it's very simple. W equals C plus C inverse. Okay. So as one application, there's quantum homology. Is isomorphic to the Milnor ring. Okay. Divided by the derivative. So now I can see what's happening here. So if the characteristic so this one here, this defines the locus where the derivative is 0. In other words, it's the ring of functions on the critical locus. So if the characteristic is not equal to 2, this has 2 points, plus, minus, and 1. Okay, and correspondingly, that's why it splits into 2 copies of the field. So one located at each. It's the ring of functions on 2 points, and if the characteristic of K is equal to 2, then there is 1 critical point, obviously. Okay. Z equals to 1. Okay. And in local coordinates, so let's say I do so W of T, so T, Z is 1 plus T, okay? It's 1 plus T plus 1 plus T inverse, which you expand in a geometric series, and it gives you T squared plus T cubed plus T to the 4 plus T to the 5. Okay. So in particular, I'm going to use just a formal coordinate here, so double bracket T, formal power series near this point, which is okay. So And yes. So when you take the derivative here, right, the t squared term disappears, 2t, but 2 characteristic 2. Here you get a t squared, and then the higher order terms don't matter when you divide out by what it generates here, so it's okay. Is everybody with me so far? Okay? I wanted to point out something here. So in characteristic 0, if you have, if this would be a function with a non-degenerate critical point, you can always change locally variables to just make the function plus t squared, plus or minus t squared, in this case here plus t squared. But in finite characteristic, that's not necessarily the case. So this term here can't be moved. That's very easy to see. The only coordinate change that could possibly do something is to replace t by t plus t squared, and then when you look at it, you see that it does nothing to the cubic term. So I would like to explain to you what the meaning of this fact is here in terms of symplectic topology. So we had a closed symplectic manifold. We had the quantum homology ring. Now suppose that I have, so this is a two-dimensional manifold. I think that, since always time, it'd be interesting in symplectic geometry, Lagrangian submanifolds. Subject to certain other conditions that I'm not going to specify. So these are n-dimensional submanifolds which are isotropic for the symplectic form. And then there is sort of a version of this one here, of quantum homology, for these Lagrangian submanifolds, which I'm going to write like this. So the third homology, which is, well, you can think of it as the ordinary cohomology deformed by contributions which are now maps from a two-dimensional disk, holomorphic maps on M with boundary conditions on L. So if there are no such maps, all such maps are constant, you just get back the ordinary cohomology with its ordinary ring structure. Okay. So you'll notice that here I put quotation marks in here. So this deformation is in a much more serious sense than in the case of quantum cohomology. So it can also deform the structure of this as a vector space. So it's better to think of there's a spectral sequence starting from this one here, which converges to that. And during that spectral sequence, the vector space can become smaller.
In case if I take L to be empty, I don't recover a region.
No, if L is empty, it's 0.
So you don't recover a region.
Yes. Yeah. If you take L to be 0, empty, there's nothing. Okay, so
L is empty and M is empty because dimensions, right?
Well, it could, and the empty set has any dimension. Because it's locally modeled on any Rn. Yes, but maybe the example is like this. If you took the diagonal inside M cross M, where you take omega M cross 1 minus 1 cross omega M. Okay? Yeah. That's a symplectic form, then the diagonal is Lagrangian, and in that case here, the third homology is just a quantum homology. So it's actually a generalization. But the example that I want to look at is really where L is S1 inside M, S2, equatorial circle. Okay. So a circle that divides the sphere into two parts of equal area. So in this case here, it's actually true that the flow cohomology is the ordinary cohomology. Okay, so this is probably better use a different symbol here, C. So this is the generator of degree 1, and that C squared is equal to 1 in the ring structure on this flow cohomology. Again, because, well, it's it's the circle on the equator. There's two obvious holomorphic disks, but because of the way that the definition works out in terms of ordering of points, only one of the two disks contributes.
Oriented maps or something.
What's that?
Oriented maps or something like that?
Can I not say this? Okay. So, okay. So, so in terms of, okay, so now I would like to say what happens here in terms of mirror symmetry. So as I said, the quantum cohomology can be recovered by sort of taking essentially the ring of functions on the critical locus. So the flow cohomology of this particular thing, okay, so the ring structure is that C squared, the interpretation of this computation in terms of here is that C squared is, well, the second derivative of this function at the critical point, Z equals 1. Okay. Well, of course, the second derivative of a function in characteristic 2 is 0, and generally speaking, it's even, so half. Okay. This is a typical thing in you say, wait, I'm not allowed to do this, but this is a divided derivative, which is very typical of the characteristic 2 thing. So remember, so in local coordinates, so Z equals T plus 1, so Z equals 1 corresponds to T equals 0, so W of T is this one here, and then the second derivative divided by 2 is of course 1. Okay. Now, what I wanted to say to you is the following thing, is that so this is a cohomology level structure, but in fact, like pretty much every cohomology level structure that you'll ever come up with, is there is okay. Alright, but let me just erase this. So we decided that the flow cohomology at L is K C squared minus 1. Okay, and but there is so in fact there is an underlying chain level structure of the co-chains, which of course I haven't explained to you. And because there are this differential graded algebra, sometimes you have secondary products. Okay? Okay. So if I assume that the characteristic of A is equals to 2, which makes these are sometimes ambiguously defined, but in that case, the one that I'm going to write down is uniquely defined. So this is a third Massey product. Traditionally, they've written like this, and this is actually non-trivial. So this means that the co-chain level structure has some information that the cohomology level structure did not see, and this information here is actually, in this case here, it's encoded in terms of the third derivative divided by 6. So the fact that you could not remove this one here is an expression of something that's a fact about flow homology. It's not an immediately obvious fact, but this is a special case. Of a recent theorem by Jack Smith, which relates the sort of higher order product structures to the Taylor expansion of the superpotential.
So your notion of massive product doesn't require the first one to be zero.
Okay, that's a good point. So the usual notion of massive structure requires this product here to be zero, right? Well, so there's some things I would have to say. Let's say like this: if you replace C by C minus 1, then the product would be 0, and then it would become something which you're maybe more used to as a massive product computation. But in any case, the massive products are ambiguous, right? You have to divide by something to make them well defined. And if it's a characteristic is not equal to 2, what you have to divide is everything. Okay? If the characteristic is 2, what you have to divide is by 2 times something, so it's well defined. So this phenomenon only exists in characteristic 2. Corresponding to the fact that, if the characteristic is not 2, I can change coordinates here to make the cubic term disappear.
This is kind of a infinity massive?
Well, maybe, but you can think of it as an ordinary massive product. It's not a problem. Just change C to C minus 1, which is nilpotent in characteristic. Whose squares are in characteristic 2. Very good. Okay. So,
is there any interpretation in this case of Lagrangian in the mirror picture?
Yes, the Lagrangian is. There is actually an interpretation of the Lagrangian in the mirror picture, but I would have to introduce, say, matrix factorizations. Okay, so it actually corresponds to the obvious way of factoring this superpotential here into t times t plus t squared plus and so on. And I could do the whole computation on the mirror and show you how this massive product appears, but it just takes way too long. Okay, so there is an interpretation of this Lagrangian. Now, okay, so this is fine, but you can say, well, we didn't really have absolutely no desire to think about the symplectic geometry of S2 because it's too trivial. Okay, so your next example would be M equals CPN. Okay, and in that case here, the quantum homology so again, you have the usual degree 2 generator. So if you have ordinary cohomology ring, this would actually be 0. And because there's a line through any 2 points in CPN in the quantum cohomology, this is actually equals to 1. Okay. Okay. So the mirror superpotential so now it's a function of n variables, and it is this one here. Oops. Okay, maybe. Okay. Okay. Which is a generalization of what we saw before.
This is
Yes? Okay. And so if you have the characteristic k equals to p, okay, so if p does not divide n plus 1, then W has p critical point. Okay, which are distinct critical points. They actually have non-degenerate Hessians. If p divides n plus 1, then some of these critical points will coincide and will have a much more complicated local structure. And
n plus 1 critical point?
Excuse me?
Maybe n plus
has
1.
has n plus 1 critical points. That's good. Then in fact, they're
k to be large enough.
the n plus first roots of n plus 1. Yes.
So you need k to be large enough to contain enough roots of unity or something like that.
Okay.
Yeah.
So the consequence of this one here is the following, that if you have L in CPN, so there's a condition here which I've been using all the time, which is monotonicity of Lagrangian submanifolds. I'm not going to explain what this is. And if you have this thing here, so this situation is quite different from before. Even under this assumption here, which is a topological assumption, we have no idea what all the Lagrangian submanifolds of CPN are. Okay, there's even an enormous amount of effort has gone into the last 10 years to understand Lagrangian tori in CP2, and I think conjecturally we now have a complete picture, but it's enormously complicated. Okay, but here is a but if you work with a coefficient field whose characteristic does not divide n plus 1, then because of this, the superpotential sort of degenerates into something with very distinctive, very simple critical points, then the Floch homology of any L is a semi-simple algebra, which means that, now I'm not going to get called out by the number theory people, if you pass to the algebraic closure, is a direct sum of matrix algebras. It's not necessarily commutative, this one here, the quantum homology is commutative. It's a direct sum of matrix algebras. Or, I don't quite know how to say this. Okay. So there, okay. So this is good. So, so you can use this as a starting point to try to understand the topology of Lagrangian submanifolds. And there will be primes where there are exceptions. Okay? So a typical case is inside CP3, there is no RP3. So, okay, so let's do an example here. Sorry, now I'm going to place the mirror symmetry. Okay, so just the real locus inside CP3, and then, okay. So if you take characteristic 2, whoops, say P equals 2 as a characteristic, then that will be similar to the S1 that we wrote down, which was the RP1 in RP2. So it's C to the n plus 1 minus 1. Okay. Sorry, C to the 4 minus 1, yeah. Okay. Which is definitely not a semi-simple ring, because it's C minus 1 to the power 4 equals 0. And if P not equals 0 to its 0, this can actually happen, which is 0. Okay. Because essentially there's not enough freedom for it to actually become any other semi-simple algebra to see that. Okay. This is my, this is the sort of accessible part of the talk. There's some geometry, but it's all done by saying, okay, I take this function and I reduce it mod P. Okay. Now, questions would be good. Okay, there will be a sudden acceleration in the direction of arithmetic geometry.
So, is there general phenomena for symplectic manifolds that for all but finitely many primes, this is semi-simple? Everything is semi-simple?
Oh, no way.
No.
I mean, there are many cases where it's not semi-simple for any prime. Cases where not deformed. But the usual principles apply, right? Which is that there's some behavior which is typical for all but finitely many primes. Okay.
So,
yes.
So it's very rare that isomorphic end of any object is semi-simple. So here you're saying that for Lagrangians, particularly.
Actually, the category is a semi-simple category.
Just prime.
So the whole everything decomposes
Okay.
into this semi-simple thing. I just don't want to talk about categories. Okay. So now. So we have X, which is an algebraic variety defined under K. Okay? And all right. So what I want to do is I want to look at its automorphism group. Okay, more precisely, I want to look at, my notation is somehow slightly non-standard. Okay, so I want to look at the formal neighborhood of the identity. Okay, so this means that. Sorry, this is horrible notation, okay, but I hope you'll all forgive me. Okay, so I have so this is equals formal families. So we start with the identity. There's some formal parameter here. And you just write down a formal family of algebraic automorphisms of the variety. It's like a Taylor expansion of a family of automorphisms. And then you stop because you declare t to the n plus 1 to be equals to 0. Okay? So if m is equals to 1, I should probably put like a dot here or maybe a hat, various things. But I think we can survive it. Okay, so these are just first order deformations of the identity, also called infinitesimal automorphisms, also called vector fields, or more precisely, derivations of the algebra of functions. Okay? So you can think of them as vector fields. Right? So you can think of the higher order ones as some sort of nonlinear generalizations of vector fields. Okay, you can also set m to be infinity, and then you should take, so maybe I should put a double bracket here. Set m equals to infinity, then you take formal automorphism of all order. Okay. Of course, you can compose automorphisms. I can truncate at some order. I could do the formal expansion to all orders. So each of these is just a group in the ordinary set. You take, two automorphisms and you compose the automorphisms. So for n equals to 1, this group structure is just addition of vector fields. Okay. Now, in characteristic 0, this isn't vastly interesting simply because if you take an algebraic group and you take its formal neighborhood of the identity, that is completely determined by its Lie algebra, so it's completely determined by vector fields with a bracket. But in characteristic P, this is far from being the case. Okay? So, okay, so there's one thing about this, so this may be a little bit mysterious, but there is one part that I can explain to you. So say that the characteristic K is P, okay? And I want to look at this one here. So it's the expansion up to order P, and I want to look so this is a group, so in particular I have iterates, so in particular we have k-fold power endomorphisms. Right? You take an element and you take its k-fold power of in this group. Okay? And what I want to look at here is the p-fold power. As you can can think in characteristic P, if you take P-fold powers, there's all sorts of magical cancellation where things sort of go away. So in particular, if you looked at, if you just reduce it to order T squared, as I said, it's addition of vector fields. So if you take, P times the same vector field, that's 0 in characteristic P. And in fact, it's a lot better, which is, okay, so we can sort of truncate mod P squared, right? We forget everything of order P squared or higher, and then we get, excuse me, yes?
T squared.
T squared, sorry. We just get a vector field, okay? And it turns out the image of this is just determined by this vector field. So you take, there's multiplication with T to the P, okay? So the only term here that's actually non-zero is the T to the P term. And what it is here, this is a well-known phenomenon, so that if you have, you have a derivation, I don't know what to call it, it's called phi, the derivation. So if you have a derivation of a ring, a commutative ring in characteristic P, you take the pth power, actually not commutative, any ring in characteristic P, you have a derivation and the pth power, just differentiate. Strangely enough, it's not a differential operator of order P because of cancellation between derivatives. It's again a derivation. Okay? And this is this one here. So this part here, this is the pth power operation. This is the part that's actually the simplest to understand. So let me give you an example.
In the formula, you will take this, if you take ID plus T1 plus whatever, you will get here,
that's right.
After this, you get ID plus T to the P times the Frobenius image of P1.
It's not, oh God, so I don't know what to say this. Let me call this. This is not, people always say
restricted.
That's because, well, what do I write here?
I think there was square brackets.
Square bracket, sorry, square bracket. It's nothing to do with, it is Frobenius linear, but it's, the important thing is the power. Okay.
But the final result is 1 plus
this 1 plus T to the P times this one here, exactly. Okay? And so this is the part of the formal group, of the group structure that's easiest to understand, I think. Because this is a linear operation. So let me give you an example here. Okay? So the most classical example is when you say C is a non-singular G+1 curve. Okay? So let's suppose after fixing an FP point, so this becomes an elliptic curve. Okay? And so in this case here, we have so the automorphism group of C. So this one here, so the elliptic curve acts on the curve here by translations. And so this one here okay, so this is the pth power maps. So these are, of course, this is what's called the formal group of the elliptic curve, this group that you get. I need more space, obviously. Okay. Okay, so now when I specialize down to vector fields, right, so derivations of OC, so this is one-dimensional, there's just the one invariant one form on your elliptic curve, and okay, here there's T to P, here there's truncation. And so this is multiplication with something which is called the Seidel invariant. Veil. There you go. So the Seidel invariant is, so this is an element of Fp in this case here. You can think of it as P plus 1 minus the number of Fp points. There you go. Okay? So this has some number theoretic meaning. I have to say that personally to me, the connection between the formal group and the counting of points mod p is a little bit of a mystery, but it's just because I'm not much of a number theorist. Okay, so you can do this actually explicitly. If I give you a genus 1 curve given by an equation, you can write down the group structure elementary in terms of the coefficients, and then you can read off the number of points mod p from this group structure. By the way, of course, this is an element of fp, so maybe the p here is superfluous, but the point is this number here is actually quite small. It's like less than 2 root of p, so it's kind of nice to write this way. Okay, so now I'm going to go back to symplectic geometry. Okay, so if you had a symplectic manifold, okay, and suppose that the mirror was not a function but an actual variety here, okay, so then the that it's non-singular smooth over K. So the derivations of OX, so these are sections. So they sit inside what I would call the odd part of the Hochschild homology of X, which is the direct sum of the exterior powers O, P, and Q are I and J. And here I'm assuming that P is bigger than the dimension of X, otherwise I just wrote down a horrible thing. Okay?
P is the characteristic.
P is the characteristic of the coefficient field. I mean, the Hochschild homology is always defined by this writing it out as exterior powers of the tangent bundle. That only works if the characteristic is sufficiently large. But anyway, so this is part of this, and this one here has a very simple meaning on the mirror symmetry. So I only used part of it, but I could have used all of it. So this is the odd dimensional homology of X. Okay?
I should ask this earlier,
Yes.
but somehow should we be thinking about the mirror as being defined over Z or over any field I choose? Or
well, so in principle, the mirror is defined over Z and therefore over any field that you choose. It occasionally can be an object of derived algebraic geometry. So I'm trying to just work over one FP at a time, because my experience is that if I say it's defined over Z, I get frowns from number theorists about bad primes for elliptic curves. Okay? But this is not a problem here, because this everything is in some sort of generalized geometry. Okay, so the question is, what is the, okay, so this is, so you can think of the derivations, which was the first ordering automorphisms, as mirror to this one here. How about the truncations to higher order? Okay, so we have this quantum homology of M, right? But it's really the homology of some differential graded algebra. Let's call it A of F. And using this one here, I can make the analog. So I'm sort of, I'm trying to make the, the mirror symmetry would be the formal automorphisms of the mirror, but I'm sort of doing it here, so they're not going to be automorphisms of the actual symplectic manifold. Yeah? Mirror symmetry doesn't really work this way. But there will be a set, okay? So MC stands for Maurer-Cartan of M, and again it works, you put this thing here, okay, and I define this one here to be a set of solutions of the Maurer-Cartan equation the Maurer-Cartan equation is this one here. In this differential graded algebra, tensored with kt
What's the equation? Is it just
equals 0.
Yeah,
Okay. Tensor, okay, I'm sorry, I was distracted by this one here. T times kt over t to the n. So they are, these are things that have no, I don't know how to write this down. T, k, t over tkt divided by t to the n. Okay? So these are series that have no constant coefficient term. So if you say alpha is equals a1t plus a2 squared plus and so on. So then this equation is dA1 equals 0 and dA2 plus a1 squared is equal to 0. Okay. So they are, so to first order, if you set, so this is in t, this is the t squared term. So if you set t squared equals to 0, so for lowest order, it's just the equation for a cocycle. And there's actually an equivalence relation on the set of all solutions, which gives you just cohomology, so alpha in is an odd dt. Otherwise, this doesn't make any sense, because if alpha is even, this is odd, and that's even, and so that's finished. Okay, so the first order thing is essentially it's a nonlinear generalization of cohomology. So then this thing here is a set for any n. Okay. So these are, simple, I don't know what to call them, quantum Maurer-Cartan solutions. At order 1, they're just the odd cohomology of the manifold, and they are otherwise there is a set. And so the first fact is this one here. So I should be able to compose this. Okay, so this one here. Is a group. Or it carries a natural group structure. For m equals 1, it's just addition on odd cohomology. It's not interesting. For higher m's, it is kind of a pain to work with. So to this day, I do not actually know whether this is commutative or not, this group structure. Okay. Of course, the automorphism group of a variety, generally speaking, is not commutative. Okay. But the mirror varieties have additional structure, they're Calabi-Yau varieties, and this is a tricky thing. So in characteristic 0, a Calabi-Yau, a variety of trivial canonical bundle, actually has a abelian automorphism group. But in characteristic P, it's not entirely clear what I mean by Calabi-Yau. And I also don't know if the theorem is true about commutativity. So this is a group, I doubt it actually. This is a group, okay, and now, so God knows what I can, this group tends to be hard to compute, but we follow this thing that I did in number theory, which is to look at the Pth power maps. Okay. So I truncate to order P, and here I have the Pth power map in the group, so I just take the element and I multiply it with itself, P times. So when I truncate to order 1, I just get the odd dimensional cohomology of the manifold, whoopsie, and here. Here I multiply by t to the p. Here I truncate. And now there should be some map here which fills this in. And this map, remember in the number theory context, this was sort of the p's power map for derivations in characteristic P. So, you know, maybe if you're a homotopy theorist, you know that this P's power map has a sort of homotopy theoretic interpretation. It's sort of a Cohen operation on an E2 algebra. Anyway, I'm getting too abstract here. Let me say briefly what this is, where psi m. And then we'll do an example. Okay. And unfortunately, it's the thing that already drove you nuts last time.
H odd is like the first, it's like multiples of t, right?
What's that?
H odd here is like the multiples of t already.
That's right, it's truncation mod t squared.
Yeah, but then if you take multiple of t and then you multiply by t to the pth, you get 0 in t to the modulo.
Okay, maybe I'm not quite saying this right. No, yes, multiple of t, but I can't divide it by t, right? I mean, a multiple of t is t times this.
Yeah.
So maybe I should call it multiplication by t to the p minus 1. I think, you know, you got it right what you said last time, that, you know, I just insert whatever I have here as the t to the p coefficient. Okay? I never know what to call this map here. So, and also, okay. So, this one you can ignore. It's a constant times the t to the p minus 1 over 2 coefficient of, so this is times of the quantum steamboat power operation. You know, it's the funny thing is that it's this quantized version of Steenrod operations on cohomology, which is the same one that I used in the last lecture when discussing Hamiltonian dynamics. Okay, somehow.
So then when p is odd, it's a power of t. When p is 2, it's
when p is 2, it's t. So this is, I forget, it's part of, yes. When p is 2, it's square root of t, which is theta in the nomination of the last lecture. But if you don't remember anything, just think of it. It's a certain Steenrod, one of the, there are, you know, many, as in classical, you know, there's a whole bunch of Steenrod operation. This is a particular one. Okay, and the normalization factor depends on my conventions, but never mind. Okay, time for an example. Okay, I lovingly put it here, but I lost my eraser. There you go. Okay, so this example, so now this is Q psi m. So this is an operation on odd-dimensional cohomology, and my example is not a bad one, is m equals CP3 blown up as an elliptic curve. How does the elliptic curve lie inside CP3 as an intersection of two quadrics? Okay, so or m inside CP1 cross CP3, a hypersurface of degree 1, 2, which is the same thing. Okay, so CP3 blown up on an elliptic curve. So it looks like the, 0 and 6, k squared in degree 2 and 4, and k squared in degree 3. So this piece, okay, so this piece here is the odd, you know, topologically speaking, because you're blowing up an elliptic curve, which is a two torus one. So this is the cohomology of the two torus. Okay, so. And so this Q psi m is some constant that depends on P times the identity on this odd-dimensional cohomology. Okay? And this is the constant. So this is strictly speaking Q psi m as a multiple of the identity. Sorry, this is a horrible way of writing it. Okay? And these are the constants for various primes. Okay? And it goes on and on and on. So, once you have those, you go to your friendly number theorist, in the case Björn Poonen, and you say -1, -1, 1, 0, -4, 2, 2, 4, what? Okay? And he comes back and he says to me, well, these are the coefficients of q to the p in this modular form here. Okay? So, q to the p coefficient modulo p. Okay? And I say, Björn, well, there should be an elliptic curve here, but I don't know which one. And he tells me that there is a database, the database of elliptic curves and modular forms, where I can look up which elliptic curve I am. So these things here so these are the Hasse-Weil invariants. Well, for an isogeny class of elliptic curves. So e.g. this is the genus 1 curve, but this is the one that I can remember easily. It's x0, x1 plus x2 squared plus x3 squared equals 0, x0 squared plus x1 squared plus x2 x3 equals 0. This is the linear set. Okay? So these are the Hasse-Weil invariants over this. So because of the connection that I made all over the place, this elliptic curve should actually be somehow in the mirror. Okay? So in fact, so mirror symmetry for this manifold is in a sort of strange state. It's never really been proved, but it's got the various partial results. There is a superpotential.
The manifold M is
CP1 cross
blown up in this curve.
Yeah, no, because this is the mirror. See, when you do the symplectic geometry, it doesn't matter which elliptic curve you blow up. It's topology.
Yeah.
Okay, it's blown up. It's independently what elliptic curve you blow up. The manifold's always the same. Okay, but the mirror always involves this one here. Okay.
Okay.
So the mirror superpotential, and the critical point, critical locus of W. Well, at least it contains as a risky, because we don't. It's not completely being determined. But we have like a superpotential of a particular open set. It contains as a risky open subset of, well, C divided Z2 cross Z2. So it wasn't quite that one, but the curve isogenous to this, which is the same thing. I can write down the equation for this one here, which is just more complicated. Okay? So I think this is a win. It shows that I can use this mirror symmetry inspired thing, involving somewhat non-standard operations on the homology of symplectic manifolds to recover arithmetic information about the mirror. Well, even if I don't know mirror symmetry, there is arithmetic information is clearly being produced here. All right. Thank you very much.
All standard operations have some kind of nice arithmetic interpretation. This operation has a kind of coincidence, meaning that the scheme-rod operations, you can think of them as operations of the infinity algebras. Yeah.
But the E2 algebras only have part of the operations. I mean, they only have this. There is an arithmetic interpretation for all the quantum steam-rod. It's somewhat more difficult, so I'm not sure what it actually means in classical algebra. I mean, I can write it down. It's just like the pth power of the derivations. There's strange things you can do with differential forms and characteristic p. They clearly have some meaning. I don't know what they do in terms of number theory. It's an open question.
But they always correspond to kind of modular forms.
I think this is kind of a...
What is interesting, most interesting is not that for every P you have an interpretation, but there is some interpretation which goes over P, Do you expect anything like this?
No, I mean, this is, certainly true that since, as Roma asked, the mirror is defined over the integers,
Yeah.
and the mod P reduction just enables me to extract this information, but there is something that's, whether it's not going to be a modular form in general, that's like an issue here with elliptic curves,
Okay.
but something interesting having to do with the global geometry.
Okay, but this theory with mirror defined of integers, is it some special cases of some spaces without moduli, or I know you consider something very basic, as you told elliptic curve doesn't matter, for example,
No,
just special phenomenon of, very, or you
no, I mean, it's just like any space has cohomology defined over the integers, right?
yeah,
So I mean, there's some technical issues I don't want to get into, but generally speaking, you expect it to be always defined. Well, not always, but yeah. With some technical assumptions, you expect the mirror to be always defined over the integers. So the mirror always has these strong rigidity properties. The technical assumption, let's say it like this. So the mirror, well, I'm not going to pretend to say it.
But
Yes.
But on the other hand, in some settings, the mirror is a symmetric picture. For Calabi-Yau, you should be seeing two Calabi-Yau and twice together back. So it's a little bit.
Yeah, that's a bit of a misunderstanding, I think. Yeah, so it's not exactly, because as you said, one side has strong arithmetic properties, the other side lacks any arithmetic properties whatsoever.
That's
Because it exchanges, I mean, you could say any space is arithmetic in the sense that its cohomology is defined over the integers, right? So it just changes that notion of arithmeticity against the notion of being defined over Z. But it's not symmetric in that sense. Yes?
So this formula that you gave for psi m as the t minus 1 over 2 power of t is very similar to the classical formula for the Hasse invariant in terms of the formal group for the elliptic curve.
Yes?
Yeah, so my question is this, yeah, exactly. This formula is, I mean, there's a classical formula for the Hasse invariant. It goes exactly the same thing in terms of the formal group of the elliptic curve. So is this like related to a proof of this, or rather my question is this observation of Bjorn Poonen an observation or a theorem?
Well, sorry. So what I'm, okay. So there's, as you say, there's good theoretical connections between the things that I did and things having to do with the formal groups.
Right.
Okay. And then from there to the actual counting points mod P. Of course, it's a theorem, but I'm relying on number theoretic facts, and I do not know what the mirror. I would love to know what the mirror interpretation is of this.
My question is
Yes.
simply in this one example.
Yes. Yes.
Okay, that you added.
Yes.
You said, okay, so you compute the.
Yeah. No, this is a theorem for all P.
This is a theorem for all P.
There's a theorem for all P. I can write down the formula for all P. And
okay,
it's
so is this theorem related to the fact that this formula that you wrote down here is very similar to the formula
Yes.
for the Hasse
Yes.
invariant
Yes.
for the formal group of the elliptic curve?
That's correct.
Okay.
Yes. Yes.
So do you have examples where Hasse with the matrix of a hygienous curve comes up?
Not yet. Okay. I have some examples of other arithmetic groups, and I have some examples where other things come up. I should do an example where I have more than two, like H3 is a four-dimensional or something, and then I should see what I get. I'm a lazy person, yes.
Could you say just something about the group structure and marker convolution?
Okay. So the question is, why is the set? So if you have a differential gradient algebra, you have a set of Maurer-Cartan solutions, right? But in this case here, you have a group of Maurer-Cartan solutions. This is a general property if your differential gradient algebra structure is enhanced to an algebra over the operands of chain on little disks. What they sometimes call an E2 algebra or even a 2 algebra. Okay? And in this case here, because quantum cohomology is defined by putting points on the sphere, right? You have like marked sphere and you put marked points on the sphere, And so it's natural that you can let the mark points wander around. So obviously it is an E2 algebra. That's maybe the best thing I can say.
Questions?